recording.
Okay. So it's a great pleasure to us receive Professor Luis Gustavo Farah from Universidade Federal de Minas Gerais, in BH, in Belo Horizonte, in Brazil. And today he's going to talk about on the mass critical inhomogeneous NLS equation. So, Professor, thank you very much for accepting our invitation. It's a great honor to receive you here. So you have the word.
Thank you, Diego. Thank you for the presentation. It's a pleasure for me to participate on this conference, on this online meeting. First of all, I want to thank the organizers, Ana, Juan, and Diego, for the invitation. I think I participated in one of these events in Niterói, and well, I hope that we can meet again in Niterói soon. So I'm going to talk about this model, the inhomogeneous NLS equation, on the mass critical case. So let me start presenting you the summary of my talk. So I'm going to introduce the equation, say some words about well-postness, and then I'll go to the main topic of my talk, that is the existence of blow-up solutions and also minimal mass blow-up solutions. So this is a joint work with some collaborators, so Lucas Campos from UFMG and Micael Cardoso from Universidade Federal do Piauí, and also Simão Corrêa from Instituto Superior Técnico in Portugal. So let's start. So this is the equation I want to consider today. So this is the usual nonlinear Schrödinger equation, right? With a power type nonlinearity here, but I also put a function here, a potential function V, and V has this form here. It's actually a function k times x to the power negative b, right? And this function k has some properties, just basic properties, so that we can do some computations later. So we ask, for instance, that k is C1, and also it's in L infinity, and also the derivative is also in L infinity, and it's positive at the origin, right? So some other assumptions I will introduce later. So this is the model that for future reference we'll call K of X INS, okay? So from the physical point of view, this is a generalization of the classical Schrödinger equation when we consider this function K constant and B zero. So this is just the classical nonlinear Schrödinger equation, the mass critical setting, and this is this equation, the classical equation, has been studied extensively in recent years, since the 90s, let's say. So let me try to explain why the model, we call the model mass critical. So for instance, let's consider the case where k is a constant, right? It's a constant function. And then when it's a constant function, we have a scaling property, which says that if u is a solution, then we can rescale the solution to get another solution. And the fact that is mass critical refers to the fact that the L2 norm is preserved under this scaling here. Okay, so that's why we call this model the mass critical. When k is a constant, right? When k is not a constant function, then we lose this property, right? Unless k has some scaling properties, we lose in the general form, right? So we have that this equation has some conservation laws, right? the one that we call mass, which is the L2 norm of the solution is preserved under the flow, and also the energy, right? So the energy is a combination of L2 norm of the gradient and Lebesgue type norm here, but with some the weight here that appears in front of the nonlinearity, right? And just to simplify the notation, I will set this power here to be sigma b, right? I write it sigma b. So some formulas later will be cleaner this way. Very good. So the first thing that we have is that the energy is well defined in H1 because we can bound this constant by the H1 norm of the solution. How we do that? This was obtained by Genoux, a sharp version of this inequality. And he proved that we can bound this potential energy, let's say, by this combination here. So this is the best constant that we have, and then it's a combination of the L2 norm of the gradient and the L2 norm of the solution. And where Q is the unique and positive radial solution for this elliptic equation, right? So this was proved by Genoux. It follows the ideas introduced by Weinstein in this other paper. And also in a previous paper, we can also generalize this inequality for different powers here. So that's why I refer to this article here. Okay, so let's now discuss the well-posedness problem for this equation H1, right? We are always considering functions in H1, the well-posedness in H1. So let me again go to the constant case, when k is a constant. Then in 2008, so Genoux Stewart, they proved that we have local opposed in H1 for every dimension and for every b between 0 and the minimum between that dimension and 2, right? And then, well, to do this, they use the abstract theory that we can find in the Casinav's book, right? Then later, some works, starting with Carlos Guzman in 2017, and more recently with Lucas and Simão, we proved that we can give another proof of the local existence based on Strickland's estimates. Strickland's estimate is an important tool in dispersive equations, and for instance, we use this kind of proof to prove this kind of approach to prove results about scattering for this type of equation. That's what also Carlos did after this work, right? And also some works with Lucas. And then, but the point here is that we cannot go exactly in the same range. We can go, well, we need to be above 2, at least 2, and then between in this region. It's small, it's a little smaller than the other region. Okay, and this is some reference. This is Casinav's book, Genoux Stewart paper, and the paper by Carlos, and this one by with in a joint book with Lucas and Simão. Okay, so and then all these proofs for the local opposedness that I mentioned before, they work also for the equation with a function k instead of a constant function in front of the nonlinearity. If we just ask that k is in an infinity and the gradient of k is also in an infinity, so we can always bound all the estimates and do exactly the same proof for the local opposedness. In particular, we can show the blow-up alternative. That's we can show that the time of existence depends on the norm of the H1 norm of the initial data, and this implies is bounded below by this, and this implies that if the time is not if the solution is not global, then the H1, the L2 norm of the gradient must blows up as t goes to capital T, where capital T is the maximal time of existence, right? And this is what we this will be our definition for a blow up solution, right? So we say that a solution blows up in finite time, so if the maximum time of existence is finite. And then by the blow up alternative, this means that we have this limit here. Okay, very good. So let me recall some results about global verboseness in H1 for a constant function k. And for this, we can, well, our task is to bound this quantity here above, right? Because if this is bounded above, then the solution blows up in finite time according to the preview explanation. So this is the idea. So we use the sharp Gallardo-Nirenberg proved by Genoux that I mentioned before, but then we adapt this to include this constant k. Because before I mentioned that the solution will be with this k equals 1, the previous inequality. So even if k is not 1, we can have the same similar bound, because all these functions k, when we modify this k here, we take another k or another constant k here, then all these solutions are related. It's somehow they're related by, it's easy to see, just a similar easy calculation. You can prove that, for example, k of q is k1 over k to the power n over 4 minus 2b, right? So this is how all these solutions are related. So you see that if you increase k, you decrease the epsilon norm of k, right? So this is one fact that we will use later. And then another fact is that we also have that these solutions here, they behave well at infinity. That is, I mean, it decays exponentially at infinity. All these solutions. We are going to use this fact also. So if we use this inequality, then we can bound this second term here below by this computation here. Then we can put this term here, and then we have this bound for the energy, or for the electron number gradient. So if this quantity is positive, then we can bound this, right? Because then we can send this to the other side without changing the sign of the inequality here. So, and when this is positive, if, for example, if this guy here is less than this one, right? This is what I wrote here, right? So if u is in H1 and the epsilon norm of u is less than the epsilon norm of q, of k, then the corresponding solution of the constant I analysis. Right, so now we want you to consider global verboseness in H1 also for this, but in the general case for the function k, right? So this is a joint work with Michael Cardoso, and what we were able to prove is that if we have a blow up solution, then we have some concentration, and the concentration always happens at the origin, and the minimal amount of concentration is this quantity here, which is related to the solution of the elliptic equation with the constant here, the number here being k of 0. So we just need to observe the value of k at 0, right? This must be positive, so we have a solution for this equation, this elliptic equation. And then we have this bound, this concentration. So this is what we could prove, right? So, well, if this is blow up, then as you can see, so this goes to infinity, right? So we can find, for example, functions, this whole of t going to 0 as t goes to capital T, so that all the mass is inside a small ball around the origin. We can say so. This. Okay, so just to mention that Campos and Cardoso in 2022, they prove a similar result for the case, the constant case, right? They consider only the constant one here, but you can also generalize for every constant very easy. Very good. And then, well, to prove this, we use compact embedding, which says that, so if we define Lebesgue space, it's the regular Lebesgue space with some weight here, which is related to the nonlinear, to the function that we put in front of the nonlinearity. So if we have this, right? So we have a compact embedding H1 in this space. So remember that if B is not zero, I mean, if B is zero, this is not compact. Right? We can prove that this is not compact. But if B is not zero, then we have this compact embedding. And this is the main tool to prove the concentration result I just showed you before. So with this result, we can establish the global, the level that we have global solutions here. So this is the level, right? If we start with the initial data, such that the L2 norm is less than the L2 norm of this Q of K0, the solution of the elliptic equation with K0 in front of the nonlinear part, right? So, and this is very easy once we have proved this concentration result, because by the concentration by conservation of mass, this is clearly less than the L2 norm of UT, but this is preserved, so this is clearly less than the L2 norm of the initial data square, right? And then by our concentration result, this is greater or equal than the L2 norm of Q. And then if we start with U0 less than this, then we have a contradiction, right? So we cannot have a blow-up solution satisfying this relation. Very good. And some comments about this previous result is that it also holds even if the function k of x changes sign. Moreover, as I explained before, right, if you take a k, well, suppose that k0 is not the maximum of the function k. So you have k1 to be the L2 norm of the elephant norm of k, which is positive. And then what we are proving here is that this is not the correct level to find global solutions, right? Because what we are saying that we can still have solutions between these two quantities here, this and this, such that the initial data, right, between these two levels, such that the solution associated to this initial data is still global, right? That's interesting because so what we are saying somehow is that the only fact that matters for us is the value of k at 0. So this is quite different from a previous result by Frank Mel back to the 90s, where he proved he considered the same problem in the case b equals 0 for the regular or for the classical nonlinear Schrödinger equation, right? And but there he needed to assume that the function is always positive for every x, and he proved that the threshold level between blow up, global existence blow up, is this guy here. So what we are proving is that we can go up to this other guy. And so let me now go to the next topic of my talk, which is the existence of blow-up solutions. Okay, so, well, if there is a very simple argument if you assume that your solution is in the Fourier space, which is the H1 intersect with the function f such that this quantity, this function here times x is in L2. So for this, then if you assume that you are in this space, then of course this quantity here has a meaning, right? Well, we can prove that it has a meaning. The initial data is in this space, then the solution will be in this space for all times. This is what we can also prove. So this quantity has a meaning, and we can take two derivatives in time for this quantity here, and we can use the equation and see that this is kind of miracle that we have, that this is related to, closely related to the energy of the equation plus some term, right? So if we assume that our potential K is repulsive, which means that you have a sign for this inner product here, then this term is negative, right? So if we suppose that if we start with a negative, this term is non-positive, right? And then if we assume that the energy of the solution, the solution is negative, then this quantity here, the second derivative of this quantity is less than 0, right? And then we prove that, well, if we integrate, it's actually negative and away from 0. This means that this quantity here must be below an inverted parabola, for example, and then this quantity here must vanish at some point, which is not possible because we are assuming that we start with initial data which is not 0, for example. That's why this is a simple argument that says that every time that we have negative energy and a repulsive potential, then the solution blows up in finite time. So this is the classical. This was done in this paper here, and this is based on the classical argument for the nonlinear Schrödinger equation obtained by Glass. Okay, and then later it's possible to see that we can replace this space here for the initial data. We can replace this by a radial assumption, right? So this was done by Jean, 2018. It's based on this argument of Ogawa-Tsutsumi for the classical analysis equation. So this is the statement: if U is radial and the energy is negative, then the corresponding solution blows up in finite time. So this is the two works that I mentioned. And then later, recently, in a joint work with Mikhail, we were able to remove the radial assumption. So we proved that every initial data that you start with negative energy, then you have blow up. That's the statement for the constant case NLS, right? So this is all that I mentioned is for the constant case, right? So what we want to do now, this is the paper, and this was just to comment that this is interesting because there is no result of this type for the classical analysis, unless the dimension is 1. For the dimension 1, this was proved by Ogawa-Tsutsumi on this work, but there is no result for dimension greater than equal to 2. So the only result that is available is for radial data or in the Fourier space. So what I want to show you today is that we can generalize this for the non-constant model, right? And then under the same assumptions that we have before, right, including this one, and then with a repulsive potential, then every time that we start with negative energy, you have low infinite. So that's the result for the general equation. So just some comments about the assumptions. This assumption here implies that k0 is the maximum of k, of the function k. And well, if you take k a constant function, then this is exactly what we have done before in the previous work. So let me give you the sketch of the proof. Right. So instead of consider here this weight, we are going to consider a weight with this well, a general function, for example, like this. It's similar to the one that Carlos Koenig mentioned in his talk. And then you can compute the second derivative using the same strategy then, but now you still have that this is equal to the energy plus some error terms, right? And then these are all the error terms that we have. And now you take V to be, well, essentially B will, this function here will be essentially x squared, and then it's a constant function. It's like this. Right? So because, see, right, so V is 2R, and then we are integrating this, right? So we get the r squared, for example, which is this form here. Very good. And then, so if we assume that this guy here is negative, so for free, we can drop this, right? So, and also we can check by the definition of this function that this quantity is positive. Then we can write, well, after some computation, we can write that this second derivative is the energy plus something that we can make small. Well, this one we can make small just taking our epsilon small. And then also you take epsilon small, increase r, and then you can make this two as small as you want. And then, so this will not be a problem if the energy is negative. And then you need to control this term. Let me show you how to control this term. So this is the definition. We need to show that this quantity here is negative. That's the idea. When r is greater than capital R, the capital R that you have here. So we need to prove that this is negative. That's the idea. So, and then you have the same contradiction argument that I showed you before. So what we do, well, then you need to consider all the possible regions for the definition of this function V, but the worst region is this one, when R is between these two numbers here, which is this quantity, this region. But it's good because in this region we have exactly the value of the function, so you can just put it here and get one like this. Right? So as you can see, so this implies, so this guy here, this relation here implies that this quantity R, capital R minus 1, is bounded by 1 over k minus 1. So if this is positive, you can bound this from above, right? So if this power is positive, we can bound this quantity by this to that power. That's the next line of the inequality here. So all we need, then if we take epsilon very small, then this is of course negative, right? Or non-positive. Okay, greater than 2 over p. So that's why we cannot use this type of argument to treat the classical I-analyzed equation, because in the classical I-analyzed equation, this b should be 0. So yeah, we cannot have a k satisfying this relation. So that's what I want to mention about this. And then you can still refine this argument and shows that this level here is the threshold between global existence, and blow up. So we show that below this level, we have global solutions, I'm sorry, and we can prove that above this level, we can find solutions that blows up in finite time. If we have that the potential is repulsive, or also, this is more a little more technical to prove this, but we can still have this type of blow up result if you are assuming that this relation holds only around the origin, right? So this means essentially these two conditions means that the zero is a global maximum of k, the first relation, and the second one means that zero is the local strict maximum of k, so just around the origin. So this is a very nice result. So this is the difference between one of the main differences between this equation and the classical NLS equation. Okay. So this is based on this. We are inspired by this work of Mel when he considered this type of equation when k of x is just it's somehow the classical mass critical NLS equation without this x to the power negative. Very good. And then, okay, so let's go to the last part of the talk. Diego, how many minutes do I have?
I think that just a second, you have 20 minutes.
So that's enough.
10 minutes. Sorry. 10
okay.
minutes.
Okay, thank you. It's enough. Okay, so summarizing what we have proved that less than this level, which means the initial the actual norm of the initial data is less than this level, the solution is always global. And if you are just above this level, you can find blow-up solutions in finite. So this is somehow the threshold level under the assumptions that I mentioned before. Very good. So what we all want to do now is what happens at the threshold. So can we, if U is a solution that blows up and the L2 norm is exactly equal to the L2 norm of this quantity here, we say that this is a minimum mass blow-up solution, right? Because below is always global and above you can find blow-up solutions. So this is the definition of minimal mass blow-up solution. So let's try to investigate the existence or not, or no existence of this type of solution. So first, if you consider this special solution here, the standing wave, where QK is a solution of the classical elliptic equation, then we can apply the simple conformal to this solution here, which is n-orbitan also a solution. This is a solution of the equation. And if you compute the L2 norm, the scaling, the L2 norm is invariant under this scaling. So the L2 norm is always for every parameter here, it's the L2 norm of k, qk. And if you differentiate, so this goes out, right? So you have this factor here in the denominator. So if t goes to capital T, this the L2 norm of the gradient blows up. So we can easily see that by simple computation that this is a minimal mass blow-up solution for the equation with a constant coefficient. Very good. And then it was proved in two different works with two different techniques, one by Combe-Genou and another proved by Campos and Cardoso, that this is only the the only minimal mass blow-up solution for this equation up to the invariance of the equation. So this was proved first by Combe-Genou using the strategy of Mel, and then by Campos and Cardoso using the strategy introduced by Remigi and Kirai. Right? And then what we want to do, so what about the equation without constant k? What can we say? So our first result, so this is based on, this is inspired by this another work of Frank Mel here. And so we have two different results, a non-existence result and an existence result. So the non-existence result, we assume that the potential here has this property, right? So this means that you can bound from below the difference by this quantity here. And this also means that Kx, if you use a Taylor expansion, for example, you can also see that K of x is not situate near the origin if it satisfies this type of relation. So under this assumption, we prove that there is no blow-up solution, or no minimum mass blow-up solution. Why? Because, well, first of all, you consider the energy, and then we write, you add and subtract this term with K0. So you add this term here, U of K0, U0. So, and this is always, greater or equal than 0 if you are at the threshold level, right? So this means that you only need to consider or to study this quantity. And using the same argument that we had before for the concentration result I mentioned before, using similar techniques, you can prove that if you take lambda to be this fraction here, then this converges in H1 to the function Q of K0 up to this parameter here. Right. Very good. So under this assumption, then if you are outside the origin, so outside the origin, you can just bound this, right? You can bound this guy by the infinite norm, and then outside the origin, you can bound this. This is bounded, and then you rescape the function and get this. But do you know that this guy converges to Q? Right, in some way, because it converges in H1, so it converges in this norm too, because of the compact embedding I mentioned previously. So, and for Q, you can compute directly the size of this quantity, and then you use the exponential decay that I mentioned to you that Q satisfies, and then you can bound this quantity by this. And then since when t goes to capital T, this lambda t goes to infinity, right? So this goes to 0. Very good. Sorry. Okay. Actually, it goes to 0, right? It's the opposite. It goes to 0, lambda t. That's why when lambda t goes to 0, so this quantity here goes to 0, right? And then inside the origin, then you use the assumption of a theorem. So inside, close to the origin, you have a bound from below for this. So you get this. And then again, you rescale the solution using the convergence in H1, and you get this. This is just a constant, and we have this lower bound for this quantity close to the origin. But this is, but this goes to 0 on the t, right? So unless, if we're assuming that alpha 0 is less than 1, so this is actually in the denominator, right? And if this goes to 0, so this quantity goes to infinity, and this is a contradiction. We cannot have this because of this first inequality. We can always bound this quantity by the energy, which is fixed. Very good. So this is the argument. So let me now spend maybe 5 minutes that I have left trying to explain now the existence of minimal mass blow-up solutions. So for this, I assume that the function k is somehow flat at the origin, right? And I want to show that there is a minimal mass blow-up solution for the equation k of x I NLS. Okay, so this is based on this other paper of Mel, and to do this, we need a new dispersive estimate that somehow we can control the estimates at this space L sigma BD. So this is a generalization of the classical, dispersive estimate obtained by Geneva and Velo back to the 70s for the mass critical NLS in this paper here. And this is based on this, the proof relies on the Lorentz space approach using these dispersive estimate proved by Braz Silva Ferreira and Villa Mizarroa in 2009, right? So this is the paper. So with this in hand, as I mentioned before, we know that this is a blow-up solution with minimal mass, but this is not a solution of K of X I analyze. This is a solution of this equation with a constant K here. So the idea is to construct a sequence of solutions to the Kx, right, to the non-constant Ks, and then we apply a compact argument to construct the minimal mass blow-up solution. Let me try to explain this. So, okay, so for every small epsilon, so you define V of epsilon, the solution with the solution of the equation, K of X, such that at this time, the initial data has this form, right? Okay, so we use, for example, the integral formulation of the equation, and we can write the difference by this because, well, the initial time, it's the same, so we don't have the linear evolution that appears in the integral formulation. You only have the integral part, and then you add and subtract to write like this, and then you use the new dispersive estimate to get these powers here, right? So this is somehow, well, note that the same norm that appears here also appears here with some integration. This is not, we cannot use directly Gronow inequality. So what we do, we use, for example, we use first a numerical lemma, which says how we can bound this integral here times some exponential term. Suppose that this is exponential, then we can always have that this is also exponential. Okay, we have an exponential bound. But for this, we need that our L should be large. What is L? L is how far, we call the definition at the beginning of the term. So L0 is how close to the origin you are flat. Right? So I'm assuming that I'm flat in a region, in a big ball around the origin, so that we can use this theorem. And then we then compute this, and we can have a bound for the difference, an exponential bound. And then we prove that this is a bounded sequence in H1, and then we can use the compact embedding to have a sequence that converges strongly to some function in this space, also in H1, because of the weak convergence, right? This is bounded in H1, so we converge to some function also. And then we use this U0 to be the initial data of the solution. And this will be the minimal mass blow-up solution that we want to construct. Why? Because, well, passing the limit, we have this relation here, so it behaves exactly as Q. And, well, for Q, we have a explicit expression for Q, and then we can show that for Q, we have these two relations, these two limits here, and then using this inequality, we have the same for U. And then, of course, if this is true, then the part that appears at the energy, the second part that appears in the definition of the energy goes to plus infinity. But then, since the energy is converged, so the L2 norm of the gradient must go to plus infinity. So this is a blow-up solution. And of course, and to prove that it's a minimal mass blow-up solution, so we see that by the weak convergence, we have this for free, but then we must have the equality, right? Because otherwise, if this is a strict inequality, then the solution is global, that we already proved in the beginning. So this concludes the proof when L0 is large. So then what about for general L? So we just use this scaling argument. Right? So if you define a new constant, a new function k by this scaling here, you see that this is k0 for x in this region. So if we take lambda very large, right, sufficiently large, then we are in the same situation at the previous theorem. So we have the blow-up minimum mass blow-up solution, then we come back. We define a function like this, and you see that this solves the original equation, right? So, okay, so that's all I want to present to you today. Thank you very much again for the invitation.
Okay, thank you very much, Gustavo, for your very nice talk. So now we open the turn for question comments. So if anyone has a question or comment, please just do it. Okay, I have one question. Is so you prove that the solution blow up with the H1 norm, right?
Exactly.
And what about if the solution is more regular than the initial data is more regular?
But even if it's more regular, you are still in H1, right? So every time that you are in H1,
yeah,
you have blow up.
You have blow up.
Yeah.
Okay.
What we can ask is that if you have less regularity, right? Because if you have less regularity, then you cannot use, for example, this conservation law. Because to use this, you need to be at the H1 level.
Okay, and I mean, you still have blow up in a more strong norm.
More than H1?
Yes.
I don't think so, because, well, to do this, then, well, the approach that we use is always relies always in some conservation law, right?
Mm-hmm.
And then this is the conservation law that we have at the H1 level. I don't think we have others conservation law for the classical NLS in more regular spaces. Right?
Okay. And my second question is that so you have that the H1 norm blows up, but I mean, can you identify in the domain where the solution where in the space the solution blows up in time? I mean, can you localize this zone where the solution grows to infinity?
I think you can always, well, we didn't do that, but at some point of the argument, we need some restriction like that. And if I'm not wrong, what we are able to do that everything happens at the origin.
Yeah.
So outside the origin, it goes to zero. Right? So I think this is what you were asking, right?
Yeah.
So I think if you localize around the origin, then because you have this type of concentration result, see?
Yeah.
So if you are above, or if you are a blow up solution in finite time, then you need to concentrate at the origin.
Mm-hmm.
And somehow outside the origin, you go to zero. The L2 norm and probably the L2 norm of the gradient.
Okay. And I have another question is that
Sure.
You have some condition on K, right?
Mm-hmm.
Is this condition optimal or?
Well, I don't know. I don't know if it's optimal. We want to investigate what happens when K is, for example, C2, right? Because as I mentioned, like this result here, the no-existence result, as I mentioned it's this one, right? So one of the comments that we have is that this under this assumption, the function is not C2, right? So what we want to do, we want to investigate what happens if the function is C2, right? Because, for example, then in our existence theorem, you assume that the function is flat, right? around the origin. So of course it's C2, right?
Mhm.
At least around the origin. So all the behavior that matters is around the origin. That's what is different from the classical NLS equation, for example.
Mhm. And also, I mean, you are in the whole space, right?
Mhm.
And can you deduce similar result in, let's say, some
Half-line, for example.
with some boundary, let's the house space or something like that?
I don't know. I have never thought about this, but I don't know. I don't know if there is. I don't know if there is a paper, not even for the classical NLS. I'm not sure. I need to investigate.
Mhm.
But it's a good question. It's a good direction.
Okay. I have no more questions. So if anyone has a question to Professor Luis, so if not, thank you again for your very nice talk, very clear. And
Thank you, Gio.
I give the word